Now we will see convolutional neural networks. So the idea is to make use of these convolution operations in the neural networks, and to have some kind of neural network that will be particularly fit for image processing or other kind of signal processing based on convolutions. And the idea is that the filters that we saw some filters that were pretty fine. Now we are talking about learning the numerical values of these filters to achieve some results. So basically, the neural network will aim at getting the right numbers in the convolution filters to achieve good performance for classification sets. So we will define a network that is exploiting elements of the data structure. So for like sound and speech, which is basically a temporal 1D signal, we can apply 1D convolutions. And so there are like convolution network in 1D that are good to process such a signal. For images, we are dealing with spatial data, so 2D convolutions is the right model for that. And we also have video that can be processed with 3D convolutions. That's not necessarily the best or the only approach, but that's an approach that is possible to have convolutions in space and time that can be used for processing videos. The point is that with such networks, we have, in fact, a sequence of convolution stages where we apply convolutions in parallel, several filters that are applied on the current image. And we are filtering the output because these convolution operations tend to produce a lot of a big output, in fact, much bigger than the input with many filters. And so we need to somehow kind of filter the results and compress that in something that is manageable for the other layers. And we also have transfer functions and other elements. So basically, it's a really neat way to model the processing in a neural network with convolutions. And it allows to have a much more compact modeling than fully connected networks like the usual multi-layer perceptrons. And it is also translation invariant in the sense that, you know, the same object in different positions in the image will be processed in similar ways. We don't need to learn how to extract, I would say, flowers from the top left versus flowers from the lower right. This will be the same filters that will trigger that we see a flower in the image. So the idea is that in a convolutional network, we have layers of convoluted filters which are applied on different channels. So we have many layers of convolution filters, and each filter produces as output a channel, and this channel is processed by the next output. And we also have what we call pooling functions. So basically, pooling functions is to synthesize and extract, I would say, some values from more values. So it's a good way to kind of downsample the image by, say, a factor of 4. If we just take a window 2x2 and we get maybe the maximum value in this 2x2 window, that is what we call max pooling, or average pooling, which is averaging, would say that the 4 values in the 2x2 window into a single value, and that allows to reduce the resolution of image, assuming that we have, in fact, more channels and smaller images as we go through the convolutional neural network. And we also have transfer functions like we do in MLP. ReLU is commonly used, but we can use other stuff. And we can also, in fact, combine this with fully convolutional, fully connected layers that are basically the layers of MLP toward the end, using whatever transfer function that is relevant there. So it's, yeah, basically the end is pretty much like multi-layer perceptron for making classification decision, for example. So we have an example of a convolution network here. So basically, we have this kind of image in color. So we have 3 channels from that image as input, the red, green, and blue channels. So each channel is a matrix with the numerical values corresponding to the intensity of red and green and blue. So these 3 channels are given to the first convolution layer, which is applying the filters on all these channels. And we've got as results many more channels, which are the results of the application of the several convolution filters on all of these channels. And then we have a ReLU. So ReLU is basically applied on each individual values to change them. So from that application of convolution and ReLU, we've got these channels, and we will downsample them with max pooling in order to reduce the dimensionality. So we have much smaller images, but over many channels, over which we apply a new a new layer of convolutions and ReLU, which results in that thing. And then we apply max pooling, then again, convolution and ReLU, and we got to something really small that we can use then in a fully connected layers to bring up a decision about the class corresponding to that image, which is said to be samoyed here. And we have other, I would say, possibilities here with different scores that are given as output. So the idea with convolutional neural network is that we are implementing the idea of deep learning with for images. And so as such, the idea of going from like a low-level set of features to high-level set of features as we go deeper in the network and we are making use of compositionality is really well reflected in that model. As input here, we see kind of really local edge detection and texture detection filters we can get. So this is kind of different output of filters that may come from such an image. So we see here that it tends to really detect local elements that are really specific in the first layers, but we expect as we go deeper in the network, the features get more like middle level here and high level there. So in such high level features are kind of building blocks that can be used for making the classification decision with a trainable classifier. And you look at here, these kind of things, may let us see different patterns, complex patterns that may represent elements that we would like to see in the image to identify what is the class of the object here.